Hello, everyone. Welcome to today's Bright Talk session. Title is Unlocking CXL's Potential, Revolutionizing Server Memory and Performance. We're going to explore the transformative potential of Compute Express Link, a groundbreaking interconnect standard that is redefining server memory and performance. My name is Arthur Sinio. I'm the co-chair of the SNIA's PM Special Interest Group. And with me today, we have three distinguished speakers. First up is Jim Handy. Jim is a highly respected semiconductor industry analyst with over 35 years of experience. As the founder and general director of Objective Analysis, Jim provides valuable market insights into the semiconductor and storage sectors. His career roles at leading technology companies include analyst firms where he has earned a reputation for his technical expertise, accurate forecasting, and thought leadership. Jim holds degrees in electrical engineering and business administration. Also, we have Mahesh Natu. He serves as a senior principal engineer and director of platform architecture within Intel's data center and AI group. With 29 years of experience at Intel across various engineering roles, Mahesh has been instrumental in driving innovation in platform architecture. He is the co-chair of the Systems and Software Working Group for the CXL Consortium and the Universal Chiplet Interconnect Express Consortium. Since the inception of CXL Consortium, Mahesh has played a pivotal role in shaping industry standards that are critical to advancing modern computing. And lastly, we have Torry Steed. He has been the senior product marketing manager at Smart Modular Technologies since 2022. In his role, he leads product marketing efforts, defines product roadmaps, drives business development strategies, and manages advanced memory solutions such as CXL products. Before joining Smart, Torry worked at Gigatech, which was a subsidiary of Cypress Semiconductor, where he specialized in advanced memory technologies like NVDIMMs and SuperCAD modules. Torry holds a bachelor's degree in electrical engineering and has extensive experience in ASIC design, systems engineering, and applications. This is our agenda. So Jim is up first. He's going to give us an introduction of where CXL is headed, followed by Mahesh. He's going to talk about the standards and the consortium updates from CXL. And then lastly, Torry will give us some insights about the benefits implementation on the CXL ecosystem. Before we start, just an overview of the SNIA community. Consists of approximately 200 corporations with 2,500 active members and over 50,000 worldwide IT end users and professionals. So what does SNIA do? We engage technology users. We educate on compute, memory, and storage technologies. We help to accelerate standards, SNIA standards, and propel technology adoption. And we do that by demonstrations, by these webcasts such as the one we're doing today, presentations, tutorials, blogs, a lot of information that the group publishes. And this is our legal notice. I'm not going to read that, but please take note of our legal restrictions here on this presentation. And with that, I'm going to hand it over to Jim to start us off.
Thank you, Arthur.
Oh, sorry, Jim. One reminder to everybody: we'll take the questions at the end. Sorry, Jim, and we should have plenty of time for questions, so either type them in the chat box to your right, or you can ask, and we'll address the questions at the end. Thank you.
Yeah, thanks, Arthur. There's actually going to be, plenty of time for questions, and we just love it if we did hear a lot of questions from the audience. So my presentation is just a few slides, and it's called CXL is Exciting, but Where is it Headed? And there are some questions because CXL is actually a lot of different things to different people. It can do a lot of things. And what is it really for? Is it for maintaining coherency? Back when CXL first was announced, along with a number of competing interfaces that were similar to this, they all focused on coherency as being an important point. And so that seemed like that's a really big deal. But also, as the standard developed, then everybody started talking about stranded memory. If you have a number of servers and each one is equipped with the amount of memory that's the maximum you're going to need for any one application, and then they don't end up running that application, you may end up with a whole bunch of DRAM that's unused. and that's not very cost effective. And so that's another solution that CXL brings. But then there's the option of expanding memory size. I know that Torry's going to be talking about that a good bit. And with CXL, you have virtually unlimited amounts of memory that can be attached to a processor, as opposed to today's scenario, where you've got the memory limited actually by the capacitive loading on the memory channels. Another one is increasing memory bandwidth. If you can get what's in effect more memory channels into the processor than you're able to just through the DRAM channels, then that should be able to give you considerably more bandwidth than what you're able to do with a standard DDR connected memory. Supporting persistent memory is another one, and this was something that happened because of the fact that CXL and Intel's Optane memory happened at about the same time, and Intel was trying to use various enhancements on a DDR bus to be able to control their Optane memory. That was a very difficult and kind of an unsustainable model. And so CXL has hooks in it to take care of that, because even though Optane is no longer with us, the idea of having a persistent storage class memory is still one that is embraced by a number of people. And once the economics get together for that to work out right, then that is going to fall into place. Another thing that CXL supports is it can hide the differences between different DDR type DRAMs, or you could even put HBM DRAM on a CXL channel. It would be, kind of a waste of money, but that is an option. And you could even, some companies have experimented with putting NAND flash on the CXL channel. You could put pretty much any memory on there. And so all of a sudden, the processor doesn't have to have the job of being the thing that grooms the memory, that does the refreshes or any of that kind of stuff. You can just say, okay, any old memory attaches to the processor as long as it's CXL compatible. So that's a real beauty, and that frees up the processor. It gives an awful lot of extra chip area budget to the processor designers to be able to do better things with the processor than maintaining the DRAM. And then finally, something that's more sophisticated than most people use right now is the idea of passing information between processors, between a CPU and a GPU. And it's a faster interface for doing that. And CXL, especially CXL 3.0, has got built-in hooks to enable you to do that. And in the future, we expect to see very large fabrics of processors of all types communicating with each other and sharing memory with each other. And when I say sharing memory, that's the word sharing actually has special meaning in CXL, so I shouldn't use that word, but it is the idea that a memory resource is available to several different types of CXL devices, and that's memory pooling is the official term for it, and that's something that's available. So all of these things are there. The question is, how do they, what kind of an interface do they use for doing that? And the interface is basically a PCIe physical layer. The people who put together PCIe did a very good job of designing a very high-speed interface with a lot of room for growth in the future. And the only thing that is not amenable to CXL in PCIe is the PCIe protocol. And so the developers of CXL went and redefined the protocol that communicates over the PCIe physical layer. And with doing that, then they were able to put in hooks to support disaggregated memory, to enable pooled memory where, a central memory pool is then divided up between different processors according to their need. And, it's flexibly done, so you can increase or decrease the amount of memory that's available to any one processor. It supports switches for memory fabrics, and I know that Mahesh will be talking to you about some of that. And then it also allows you to have shared memory where you actually use an area in memory to trade arguments between two different processors, knowing that that will be handled coherently between the two processors. And then finally, it can support persistent memory, that it most persistent memories have different read times than write times, and CXL is able to communicate in a way that allows that supports that, whereas DDR requires you to have the same speed read as write. So what does a CXL device look like? It's actually a CXL DRAM device is a lot like an SSD. If you look at the most basic idea about how an SSD is laid out, you've got a PCIe interface that goes into a controller, and then the controller controls a number of NAND flash chips with a number of channels typically inside the SSD. An SSD might have 4 channels or 8 channels inside of NAND flash. And these channels are all controlled by the controller, but basically it's, very simple, straightforward NAND flash with a controller that talks to PCIe. For a CXL memory device, then you end up having something that's almost exactly the same because the CXL interface uses a PCIe physical layer. It just has a different protocol that it communicates by. And so that's a change inside the controller. But, it's certainly a known way that having a PCIe interface, the physical layer interface on a chip, means that you might be able to just change the firmware on that chip or maybe make some minor hardware changes to make it compatible with the CXL layer. And likewise, communicating with DRAM chips is different from communicating with NAND flash chips. It's a much faster interface, but still the configuration of these is very much the same. And so if you look at actual devices, you have on the left here a Micron SSD, and on the right, you've got a smart modular CXL memory module. That's why it's CMM on the side of the thing. And the two of them are very similar on the outside. You can just see that the connectors are different. But other than that, very similar devices. And if you look inside, both of them look about like this. This is a CXL memory module inside, and there are a whole bunch of DRAM chips. The controller is actually on the back side of this module. There are probably more DRAM chips there too. And the controller is right in the center toward the bottom where you can see all of those little vias on the PC board. So it's a very similar kind of a device from a manufacturing standpoint and from an architecture standpoint. The thing about CXL and its current current usage is that nobody seems to be able to agree as to what it's good for and what it's not good for. You have companies like Meta saying that pooling is a really important attribute of this, and then you've got Google saying that they're not really interested in pooling because stranded memory is not important. Google's argument for this is that their virtual machines are so small and their servers have so many resources that through proprietary software, they can allocate their virtual machines to a server in such a way that the server is always very efficiently used. And, all congratulations to them if they can do that on a consistent basis. I know that a lot of other people think that CXL is very good in its ability to allocate memory as a shared resource, or I'm sorry, pooled resource. I ran into an interesting paper that was written by IBM and Georgia Tech, my alma mater actually, that said that DDR is a poor answer to problems. This paper found that the queuing on DDR channels got so much in the way of doing a high number of memory accesses that going through CXL actually was a faster way of communicating with the memory than the DDR channel. So, that certainly was an eye opener for me. We hear a lot from people who have AI systems that they need to have enormous memories. And, Torry will talk to you about that again, because if CXL does allow you to attach a whole lot more memory to a server. And also GPUs, with all of their HBM or TPUs, those kinds of processors, they tend to do very long, high bandwidth data transfers rather than a bunch of short random transfers. And this very much suits the way the CXL channel works, because the CXL channel actually introduces latency to the memory, but it pumps up the bandwidth considerably. Hyperscalers like the idea that they can have any processor talk to any other processor through mesh networks that are run by CXL. And finally, we get to PC OEMs. So this is going to be something used in your PC. And that's not going to happen soon because this is actually more of a big system kind of a solution. So that kind of gives you an idea about where CXL is going to be used. It's mostly going to be used in large scale computing systems. And with that in mind, my company, Objective Analysis, put together a forecast of where was CXL going to go. And we see it as getting off to a kind of a slow start. Where it's not even going to cross over $1 billion until sometime in 2007 or 2027, and then it's going to take off well after that, and we expect to see serious penetration, getting it up to about $3.4 billion in revenues in 2028. That forecast actually. Oh, sorry about that. But there are long-term impacts that are going to come about because this new technology is available, and very useful technology. And that is that people are going to start really rethinking what their system architecture is like, as if a lot of that isn't already happening with the conversion over to AI. But we're going to see disaggregated memory, that the memory is now going to be a shared resource. With virtualization, we had processors become a shared resource, and then we had composable storage, and that made storage into a shareable resource. And now with disaggregated memory, we have memory pooling. That means that the memory can actually be a resource that is allocated between systems. And so that's the last area in a server that needed that. We'll see processor arrays and mesh networks a whole lot more. And once again, this is a big system thing. It's not something that you're going to be seeing an awful lot of in your PC. And then finally, I put down memory agnostic. You're going to see systems where nobody cares whether you put DDR5 or DDR6 or DDR7 into your system, or even whether you put DRAM or MRAM or resistive RAM. And we wrote a report on that too. But any of these memories is going to be a good match for a processor, and you don't have to buy a processor with a DDR5 or a DDR6 interface on it. You'll be getting something that's a kind of an interesting mix, because you'll be getting better memory bandwidth if you put the memory on CXL, but your latency will get worse. And once again, this is something that you'll run into with Torry. He's got some stats on that. There will be designer rounds for that. Mahesh will go into some detail about that with his slides by talking about something called CXL hot range monitoring units. This is a way of understanding which parts of the software are okay with having high latency as long as they get high bandwidth, and which ones need to have lower latency and don't require so much bandwidth. So it's an interesting problem. I'm sure that what we're going to hear from Mahesh is going to be the tip of the iceberg. We're going to get an awful lot of very new ways of looking at everything, but it's going to take a long time for this to play out. And then finally, there's just a little plug for a report that we came out with a couple of months ago. It's called CXL Looks for the Perfect Home. And this actually stresses on that first slide that I showed with all of these different solutions that CXL offered. It's a new report from Objective Analysis. It covers the perspectives of where CXL is useful, where it isn't, tells what the demand drivers are, the opportunities outside of DRAM, gives a forecast, not just a revenue forecast that I gave, but also units and price. And it's something that can be ordered for immediate download at the Objective Analysis website. And so with that, I'm going to turn it over to Mahesh, who is going to talk to you from the CXL Consortium's viewpoint. So Mahesh.
Thank you, Jim, and thank you, Sia, for the opportunity. So let me spend a few minutes just going over what we've been doing on the CXL Consortium side. So I think most folks are probably familiar with this, but just to provide a background, we started back in March 2019. That was when we released the 1.0 spec, and we've come a long way since then, right? So you see a pretty rapid development after that, right? We had 1.1, right after that. Within a year and a half, we had a 2.0 spec with lots of new capabilities, right? And we are basically moving along, right? So just last year, in December, we released the 3.2 specification, and there's work ongoing for the next version, right, within the consortium. So what I want to talk about today is some of the work we've done between the 3.0, 3.1, and 3.2 time frame, and like some of the context we have, right, that led us down that path. So there's many things we did in 3.x, right? I combined 3.0, 3.1, and 3.2 into a single, right, kind of a bucket, 3.x. But the three things I want to highlight today are scaling, optimizing memory hierarchy, and security. Just given the time we have, these are three things I can cover today. If there's further questions, there's other webinars on the CXL Consortium that go deep into various topics. Invite you to go browse through those. So the first one is the scaling, right? Jim touched upon that. CXL, as you can imagine, started at the very bottom at single node. That was 1.1. We added caching, load store semantics, right? That was the fundamentals. When we went to 2.0, we were able to go beyond just single node at a rack level, right? You could have multiple chassis in a rack that could talk to each other. We added things like memory pooling, where one of these boxes could be a memory pool, and other compute nodes could leverage or share memory from that pool, right? That was added in 2.0. We also added features like persistent memory that Jim touched upon. 3.x, we basically went one more level at going just beyond a single rack to maybe an aisle. We added concepts like switch hierarchy that you can use to build a really large CXL fabric that's composable and dynamic. So again, a lot of work that went into going us from 2.2 to 3.x. There were other consortiums that were active, for example, Gen Z, that had done a lot of work in this area. As part of the convergence, the industry essentially got together and put all the effort behind CXL. So a lot of the ideas that were done at Gen Z got merged into CXL. Excellent work there. I think we keep talking about the memory hierarchy, right? So this is kind of a familiar diagram to most of you, but let me just go over that quickly, right? So previously we used to have cache, main memory, flash memory, and hard disk, right? Four levels, right? When we add CXL, it gives you more flexibility, adds at least a couple of, I don't know, we can call it two or three different levels here. One is CXL memory that's within the server, and you can use your latest and greatest DDR5 memory, or you could use your DDR4 that maybe you bought like many years ago, but it's still pretty good. Again, look at it has low performance, but it's probably usable. And then we can also attach memory CXL to fabric and get a lot more scalability, large capacity, but generally will have worse latency and worse bandwidth because it's kind of further away from the consumer or the CPU. So these are the ones that we added. And the problem is like once you add more hierarchies, it becomes difficult for software to manage it and optimally, right, make use of it. Right? They all have different latency characteristics. So you want to make sure that these hierarchies are hidden from software to the extent possible. So you don't have to update all of your applications to kind of understand multiple hierarchies. So one thing that we did in the 3.2 spec was the concept of hot range monitoring. So when we have multiple tiers or multiple levels in the memory, people want to use a software-based tiering, right? The challenges that we saw from the industry was that the current ones required the industry applications, which is really doesn't scale, right? How many applications can you actually change, right? In an enterprise or in a cloud, right? Data center. There were trade-offs that they had to make where they had to give up accuracy versus performance overhead. If you want a lot of accuracy, then you end up by burning lots of CPU cycles, and overall you may actually end up losing, right? So that was not a good trade-off. And there was also vendor-specific item that they need to do that varied from based on the CPU vendor. And that was kind of again difficulty scaling. What we did in the CXL 3.2 was added the concept of CHMU. What it does, it enables a generic OS-based solution. So no longer need to change applications, right? One solution at the OS level, and every application that runs on top of that or workload will benefit. It works for different CXL memory topologies, right? It works for simple devices that are directly attached. It works for pooling devices that may be further away. So it's pretty scalable. And how it does it is it will offload the tracking of hot ranges to the memory device. So the CPU is no longer responsible for keeping track of which pages are frequently accessed. The memory device will keep track of that and expose the statistics to the software. The software can figure out which pages are frequently accessed and then bring them to maybe memory that's closer to the CPU, so you don't really see performance overhead, right? So software can do that dynamically based on the statistics that each of the memory device provides. It's pretty configurable, right? One of the challenge, obviously, with the Torry solution is that based on the workload, based on the environment, based on configuration, it needs to be tuned. It needs to be a little bit more, has to be optimized. So the CHMU architecture provides flexibility to software so that can be properly tuned, can be optimized for different configurations as needed, right? Obviously dynamically. In summary, I think we believe the CHMU architecture provides a more efficient memory tiering solution, and that leads to obviously better performance because the pages that software accesses frequently are easily available quickly, and overall lower TCO, because now you can use a mix of very high performance memory, which is maybe expensive, and memory that's not as expensive, maybe large generation memory like DDR4 memory that Jim was referring to, right? In a system, the overall capacity, right? You can go to capacity without paying, the cost of the latest and greatest memory. The other point I want to touch upon is the CXL security aspects, right? So as you know, as folks want to move their workloads to cloud, they really want to make sure that the cloud service providers infrastructure isn't really able to access any of their data, right? They want to make sure that any data that's running in their VM, right, is not accessible to the CSPs, even if there's some kind of attacks on the CSP infrastructure, because the data that they have is very proprietary, has high value. So what we've done on the CXL, again, similar to what the PCI Express has done, is have a notion of a trusted VM. As you can see it here, that is able to utilize CXL device resources, such as device memory, in a partitioned way, so that this memory that's in the device here is not accessible to other VMs, right? And again, it's building on top of some of the things that PCI Express has done, but extending it to CXL memory devices, as well as CXL accelerators, right? That can essentially be used to offload the computation. So now you can have a scenario where some of the model parameters can be in a CXL accelerator. It can work on it without really breaking the confidential compute requirements that the CSP clients have. So I think that was a lot of work went into this. It took many years of effort to come up with something that's secure as well as easily deployable, and we're hoping to see deployments of this in the industry. Before I hand off to the next, I will talk about one of the events that we have that are ongoing. So just later this month, we have CXL DevCon that's happening in Santa Clara, end of the month. Expecting lots of participation from industry, various vendors that are going to show their devices. will be active in FMS, obviously, like every year. Some of the details are here. Several presentations, several demos, right? As we had done in the past. September, there will be an AI Infra Summit in Santa Clara. November, we'll have an active presence in Supercomputing 2025, similar to what we've done in the last few years. So we have special a booth in there. So encourage you to come and visit us if you are around during that time. And obviously, we'll keep adding more events as we get opportunities. But again, it tended to be a pretty busy year for us. Not to last but not the least, right? There's obviously a CXL memory programming workshop that's ongoing here, both live here as well as the DevCon. And thank you for SNIA for helping with that. So with that, let me hand off to Torry to talk about the ecosystem and how it's coming along and some of the things that they are seeing as they build and develop CXL devices. Thank you.
Okay, so thank you very much, Jim and Mahesh. Jim and Mahesh did a great job of covering what's possible with CXL, what it is, and kind of the direction it's headed. What I'm going to focus on a little bit more is what's practically available right now for CXL. So what can we do with it today, and what's out there, and what are people doing with it? What are some of the results that people are seeing in the industry today? So let's jump in. So the first thing I want to talk about is some of the most obvious benefits of CXL, right? And so we may have seen a little bit about this before, but the most obvious benefit of CXL is that you can increase memory capacity per CPU, right? Very easily. So essentially right now we hit a maximum amount of memory that can be added per CPU based on how many DIMMs can be installed in a channel, right? That's a loading issue. And then how many channels can be added to a CPU, that's a pin issue, like a physical limitation of the processors. It's a very wide interface. You need hundreds of pins to connect DIMMs. And so you can't do too many of those interfaces. So now, since CXL is based on PCIe and it's a serial interface, you can actually use those serial interfaces to connect external or memory as well directly to the CPU. So that's the most obvious one. You're effectively getting more DIMM sockets per CPU when you add CXL to a system. So that's very simple to understand, very obvious benefit, but a really powerful benefit in certain applications. Another one that we get is the reduced memory cost. And the way that works is there's always a price premium for the most dense RDIMMs, especially when you get to 3DS or through silicon via technology, because that technology takes more time, more verification, there's more fallout. It's difficult to build those devices. So especially today for 256 gigabyte modules, for example, there is a premium price per gigabit, and that extends to 128 gig, even though those are available in single die packages. There's a price premium for just the high density DRAM. So what you can do with CXL is, because it allows you to put more DIMMs in your system, more DIMMs per CPU effectively, you can stick with the more cost-effective memory die or memory DIMMs and lower your overall cost of memory. So it kind of gives you this knob you can tune where you can either really expand the amount of memory in the system if you're not as cost sensitive, or you can get the same amount of memory and lower your overall cost by using lower density silicon. And then the last benefit, which Jim touched on as well, is a performance increase. And at first glance, you might think that, well, because CXL adds that controller and it adds a little bit of latency, as Mahesh was showing in the tiering diagram, you'd think, well, isn't performance going to be reduced? And the fact of the matter is, most of your latency in accessing memory comes from what Jim mentioned, which is your queuing delay. So the amount of cores in a CPU is growing much faster than the amount of memory controllers we can add to that CPU. So when your CPU is heavily loaded, the cores are effectively waiting to access the memory. They're having to queue up for their memory accesses. And CXL through PCIe can actually alleviate that a little bit. It gives you another pathway to access memory. And so we've seen some real world use cases, which I'm going to show you in a little bit, where that benefit in particular can help. So those are kind of the three main benefits. Which applications benefit the most from those? So an obvious one is in-memory databases, right? When you can attach more memory to a system, attach more memory to a CPU, you can put larger and larger databases into that same system, right? And so that's a huge benefit because you can avoid having to go to storage. The whole database can fit in memory, and you get dramatic performance increases there. Similar for high performance computing, we're getting more and more compute tasks, not necessarily including AI, although I have AI in here as well, but just high performance computing tasks that require processing tremendous amounts of data, whether that's physics simulations or biotech with genetic research, things like that. The data sets are getting very, very large. So you benefit from being able to put as much of that data into memory as possible. AI, of course, is a huge one. There's some future-looking technology with CXL, especially in CXL 3, where we can start to disaggregate the memory more, which will benefit AI. But even today, there are benefits to AI applications by expanding the system memory. Yes, a lot of what's happening with AI is happening on board the GPUs, but you've got to feed them data. And if you can feed them data from memory, it works significantly better than feeding them data from storage, right? So, and then last but not least on here is a fintech, which is kind of a specialized high performance computing application. And it can really benefit because they're a lot of times trying to process real-time data, not just data from the stock market, but real-time weather data and real-time, data about natural disasters or things like that, because they know those are going to affect pricing of certain goods. So feeding all that data into their models can help them do real-time trading even more effectively. And CXL, of course, can help with that through the bandwidth and the capacity. Okay, so we've talked about what's coming in the future of CXL, but let's focus for a minute on the kind of how it's rolling out into the industry. How is it practically being used? The first way it's being used is available with CXL 1, right? And that method, or what's available there, is you can attach memory expansion devices, CXL memory expansion devices, directly to the CPU and get more memory in the server, right? So that's kind of that capacity benefit we talked about, as well as the bandwidth benefit. That's available today. CXL 2 added switching capability, and it also allows us to do like one tier of switching, basically. And we can't do sharing between devices, dynamic sharing, but we can do some pooling. There are 1 or 2 switches in the market today that do support CXL, and those are being used to develop products now where we have a memory pool appliance that is taking advantage of that switch to connect to a handful of other host systems. So 4 or 5 other systems can access that memory pool. And what you have in that case is it effectively means you can have memory expansion within a rack. So you'll have one memory pool appliance connected to a handful of servers within that rack. And then the next phase that's coming is the CXL 3 phase, 3.1, 3.2, which, as Mahesh mentioned, is adding a lot of new capability. And one of the biggest things that it's doing was 2 huge ones. One is it's moving to PCIe 6, which gets us increased bandwidth. And then the other thing that it's doing is it's truly supporting fully disaggregated memory pools and memory sharing, right? So once we get to that generation of products, you'll see more like the architecture that I'm showing here, where not only do we have GPUs that are being shared, but also memory and storage that's all disaggregated. But I want to focus more on the first 2 because they're actually available right now, right? You could buy off-the-shelf systems today and off-the-shelf CXL endpoint devices that allow you to implement these now. So What do I mean by that? So you can actually see that here. So this is a couple of example servers. On the left, I'm showing kind of that within server memory expansion, and that exists in a couple of different form factors. There's the E3 form factor, like Jim showed, but there are also add-in cards available too. The nice thing about the add-in card form factor is it's very similar to a GPU form factor. So we can take a system designed for GPU expansion and instead populate it with CXL add-in cards, and you now suddenly have potentially a system that has massive amounts of memory on the system. And that's, like I said, very useful for some of those applications we talked about before. So those kind of servers are available now. And then what's coming very soon is the one on the right, right? That's where we're starting to see these memory appliances become available that support CXL and can share the memory to a small number of servers within a rack. Okay, I'm going to talk a little bit about performance now too. So when you think about CXL, as Mahesh showed, you think about latency as being, a major topic or somewhat of an interest. And if we look at it hypothetically, you can see that direct attached memory in a DIMM, when you put a DIMM and attach it to a CPU, the round trip latency for that device is right around 100 nanoseconds. That's pretty typical to write data to the memory and then read it back. When you go to a CXL memory module that's also directly attached to the CPU, meaning there's no switches in between or no retimers or anything like that, you increase the latency because you have to serialize the data and then deserialize it in the CXL controller, right? So that adds a little bit of latency. So you're more in the 100 to 200 nanosecond time frame. But as we saw in the memory hierarchy, that's still significantly, like orders of magnitude faster than going to storage, to SSD storage. And then finally, the next application is with that kind of in-rack memory expansion. There you do need a CXL switch, which does add more latency. So here you're seeing maybe 300 to 500 nanoseconds of latency for full round trip access. So you're almost starting to see these like micro tiers starting to develop within the CXL, within the memory itself. And it depends on how you're attaching that memory to the CPU. Okay, so that's theoretical. What about practical? So there are a number of companies that are starting to test CXL devices. So this is a CXL device that happens to be an add-in card. And this was a test that was performed on one of the CPU servers. I won't specify which one, but we were seeing right around the 200 nanosecond. And typically we see 200 to 300 nanoseconds for this middle case, this direct attached memory, right? So it's proving to be very close to what we thought it would be in theory, which is great. Next, I'll talk a little bit about bandwidth. So the other thing we've talked about in this presentation so far is being able to increase the bandwidth. So just this is very high level, very simple, overly simplified view. But when you attach memory to a CPU in the traditional way with an RDIMM, a DDR5 6400 RDIMM has a bandwidth of around 51 gigabytes per second per channel, right? So obviously you have multiple channels, so you can use some parallelism to get higher overall system memory bandwidth, but that's for effectively one channel. When we add a CXL device, in this case, we're adding a by 16, so a 16-lane CXL memory device. This device also adds theoretically 64 gigabytes per second. That's the max that a 16-lane PCIe Gen 5 device can handle. And in practice, we're seeing right around 50 gigabytes per second using Intel's memory latency checker, right? So this is showing an additional approximately 50 gigabytes per second. So it's like adding another memory channel to the CPU. Next, I'm going to talk about some real-world applications. This is actually information from a white paper that was released by Micron and AMD. It's really interesting, highly worth looking up. There's the source is listed there on the slide. But what essentially they did is they took several of those applications that I mentioned at the beginning that would benefit from CXL attached memory and did tests without CXL and then adding CXL to see what benefits they got. In the first one, it was an in-memory database application. So essentially what happened is they doubled the amount of memory in the system. And by avoiding having to go out to storage, reducing paging I/O, they were able to get a 23% overall performance increase in that in-memory database application. The middle one is very similar, but this was a machine learning application. And so this one is also memory bound, meaning they were running out of memory and having to go to storage, but it's also very sensitive to latency. So the question was, well, I'm adding CXL, but it's a little bit of a higher latency tier. Is that going to end up being worse? And the answer was no. Adding memory capacity gave a dramatic increase in performance, even though the memory you were adding had a little bit of a higher latency. So still that capacity was the dominant factor. And then the last one was a high performance computing example. This one was very sensitive to bandwidth. So this one was not running out of memory capacity, so that didn't play a factor, but it was very bandwidth sensitive. So in this case, it depended on the configuration, right? But they carefully mapped the majority of memory to DRAM, but some of the memory to CXL to take advantage of that additional bandwidth that you get. And they saw an overall performance increase of about 17%, which is pretty significant, right? It's not easy to just jump up your performance by that much on many of these applications. Okay, this is another research project that was done at the National Yangming Chao Tung University. Apologize if I butchered the name of that, but this one is looking at performance with and without CXL. And so in this case, they were looking specifically at training large language models using a method where they offload some of the data to the CPU memory, so that they're not running out of memory on the GPUs. They're able to use some of the CPU attached memory to enhance the performance. And in this case, they did an experiment where they showed with and without CXL attached. In both cases, the system had the same amount of memory, and the goal was to show that when you take advantage of CXL, which is the red bars, you don't lose any performance. Because fundamentally, in this case, even though this example used a small amount of memory, you could theoretically use significantly more memory in this system and run larger and larger jobs, and also support higher numbers of GPUs when doing training by increasing the amount of memory you have in the system with CXL. And then this is an example. This is a YouTuber who does reviews. The channel is Level 1 Techs. And he actually had one of the add-in cards and was able to plug it into a super micro system off the shelf, and it worked. And this, just out of the box, he was able to get latency right a little over 300 nanoseconds. So that's a little outside of that 200 to 300 nanoseconds that I talked about, but it does depend a lot on the CPU that you're using and BIOS and a number of other factors, but it was in that ballpark that we're looking for. And then the bandwidth that he got using memory latency checker was also right around that 50 gigabytes per second, which is what we've seen so far. So this is another one of somebody getting an off-the-shelf system and a CXL device that's available, plugging it in, getting the latest BIOS and everything, but it working and him having more memory in the system, right? So it's here. And speaking of it being here, so this is more of a reference slide that you can look at a little bit later, but the point is we have CPUs that are available that support CXL now, we have BIOS that supports it, and we have the OS gaining more and more traction and supporting CXL as well. So it's getting easier and easier to find systems, find servers, motherboards that support it, and easier to experiment with it now. So where does that leave us? It's available today. You can get off-the-shelf systems that are here and working. The benefits that I showed at the beginning of that increased capacity and everything are real, and those rack cooling appliances are coming soon. And then CXL 3 is on the horizon and will be really exciting and add even more benefits, as Jim and Mahesh went over. So that's it. That's it, Arthur.
All right. Well, thank you, Jim, Mahesh, and Torry. That was excellent information. We've got about 10 minutes left. I'm not sure if we're going to make it to all the questions. We've got about 7 or 8 questions, and I'll start with this first one, and that is, how will the CXL connections of the CXL switch be made physically possible with multiple hosts and multiple endpoints in real time? So it's a switch question. I don't know if we can answer it on this one, but does someone want to take a stab at that?
I can take a stab at that, right? So I think it's similar to PCI Express, right? So you could have switches that have multiple upstream ports that connect to multiple CPUs. They can have multiple downstream ports that connect to multiple devices, right? So it's really a well-known thing that PCIe, right, has championed, right? So I don't see any challenges, right, making those connections and architecture.
Okay.
If I didn't answer the question correctly, you can repost the question with additional
Yeah.
detail, and I'll be happy to answer.
Well, Mahesh, we're gonna post all these questions on the blog and then fully answer them. So there's not, you guys aren't done after this. You got to do some homework. But
Okay.
all right. So another question: are there standards-based work being done for the CXL PCIe over co-packaged optics for disaggregated computing?
So I will say that I know there was work being done in the
Uh-huh.
industry for CXL over optics, but I don't know about the standards effort. I don't know if Mahesh can comment on any standards about co-packaged optics, but
There's work being done in the PCI Express for transporting PCIe over optical interface. So once that happens, we'll probably just leverage that, right? As you know, right, CXL leverages all of the things that PCI does in terms of the physical layer or the form factor, right, whenever possible. So I expect that will happen. But that's really a good question. That's where we are heading to, right? It's my belief.
Oh, good. Maybe we will get to all these questions. So, okay, the next question is: will TSP be used with Intel TDX and AMD SEV SNP? Do both technologies work with TSP?
Yeah, I mean they do, right? So again, we have great participation from obviously Intel folks and AMD folks when defining TSP, right? So what TSP does is it defines the interface between the CPU aspect, right, of the TDX and SEV and the device, right? So that's the piece that is not part of the obviously CPU architecture or CPU definition because it's outside of that, and that's the piece that the TSP fills, and device vendors can build devices that then will follow TSP spec and then will be compatible with both of these technologies, right? And there's other vendors also have similar confidential compute technologies, right? CPU vendors. I think they will all be compatible. Good question.
And just briefly, Mahesh, what's the difference between TDISP and TSP?
So TDISP is what is developed by PCI Express. Again, it solves the same problem for PCI Express, meaning it will allow technology like TDX to inspect a device, verify the device is in healthy, good condition, and bring it into the dust boundary of the TD. TSP does something similar for CXL devices. Obviously, CXL being coherent, it's it's a different problem to solve, but I think we have solved the problem. I think it's ready to be deployable, I believe.
Great, thank you. So maybe Torry, why aren't we seeing the CXL Type 1 and 2 adoption by the industry?
Yeah, good question. So I think that's coming. It's just not here yet. The big interest initially has just been Type 3, which is pure memory expansion. But we are starting to see, I think storage will eventually move to CXL as well. There's definite benefits there. And then I think we are starting to see memory with processing, right, as well. So it's coming. It's just coming in a next wave of CXL adoption. I don't know if the other guys have any comments on that, but
if I can add something to it, it's Ian, the whole ecosystem has to come together, and CXL is actually pretty new, and so I'm sure that there's an awful lot of work being done that has not been announced from mostly hardware manufacturers, but also there needs to be an awful lot of software support to make everything fall into place, and all of that comes together slowly. And that forecast that I showed actually it starts with very modest growth simply because the rest of the support network for CXL needs to be put together before CXL can really take off.
And maybe Jim, you can answer this question too, but we've talked about in-memory databases as being a big use case, but there's been, are there been any announcements about SAP HANA or anybody adopting CXL with the in-memory database? I don't think I haven't seen anything.
Yeah, I haven't run into any, so perhaps there are, and I've just missed them. But that's something that hasn't really, it hasn't come my way. Perhaps Mahesh has heard of something.
I believe SAP has published a paper. I seen it like a while ago. So there's some work going on there. Yeah, I mean, they would benefit from more capacity, right? They like as much memory capacity as they can get, right? So CXL definitely is something that would benefit.
Okay. I'm going to make this the last question. So do we expect GPUs to support CXL? Without that, the AI use case seems highly limited.
So I'll take a stab at just getting it started, but the short answer is no. We don't really expect GPUs to support CXL. So I don't see GPUs talking with CXL memory directly without possibly once it's fully disaggregated. It's possible you could have a layer that's where it's sharing information there, but no, I don't think it's going to be GPUs directly supporting CXL. It's more about, does memory expansion for the system itself aid in AI use cases? And I think the answer is we are seeing evidence that it does, but how much that plays out, we'll have to see.
All right.
Yeah, I haven't really spoken with GPU vendors about this, but my understanding was that one of the benefits of CXL is that it makes it easy to fill either the GDDR that's on the GPU board or to bring in data that can go into the HBM. So it seems to me like there'd be an opportunity for that, even if it's not something people are speaking about now.
It's possible. Future.
Let me quickly add a couple of minutes, right? So
go ahead.
There's two uses I see, right? So GPU, when they want more memory, they could go use what we call unordered I/O feature of CXL to go over and reach into CXL type 3 memory and therefore get more memory expansion, right? So that's one use case. They get more memory and second use case is GPU actually using CXL coherency to communicate with the CPU. So they are cache coherent with the CPU and they can quickly exchange data back and forth, right? Again, both require heavy lifting, lots of software enabling. So, but I think those use cases do exist. It just takes effort, right, to go and enable those and get the benefits.
Great. Thank you. That's a good place to end. So thank you, Jim, Mahesh, and Torry for working on this presentation and making it available. We are going to post the questions and the answers to a blog. Reminder to our attendees, if you could rate this session and give us your feedback, we would appreciate that. We are going to have this blog here, as you can see here. A couple other events coming up. The FMS is coming up, the Senior Developer Conference, and SC25 in November, and then a lot of online information. So thank you to our speakers and everyone who took time to listen to this. We appreciate it and hope you found it worthwhile. And thank you all for your time.
Thanks a lot, Arthur.
Thank you, Arthur. Thanks, everybody.
Thanks, guys.